In this recording, I'd like to explain the solution of the example 7.13 of textbook named Design of Analog CMOS Integrated Circuit, written by Razavi, which is second edition of the same text. And the problem goes, there's a VDD up here, and current source, ideal current source, current is I sub 1, and input transistor NMOS M1 is there, and V in equals there, and it is feedbacked from B out there, here, and the feedback is consists of register whose value is RF, and NMOS has a geometry producing transconductance GM. The value is represented by GM, and in this case lambda equals 0. Lambda is channel modulation coefficient and or back bias coefficient or substrate effect coefficient, which means R out or GDS of M1 equals almost going to infinity. In these conditions, what we need to calculate, derive the expression of input referred noise, voltage, and current. On this textbook, there's already one solution utilizing one of its represented procedures. There's two procedures using two extreme cases. One is input shorted. The other is input opened. Input shorted and also output shorted procedure is used in this textbook, and input opened way is assigned for the readers, and one hint is commented about the V out V noise voltage, output noise voltage, which is V sub N2 out squared bar. V sub N2 out squared bar is given in this textbook, but other than that, you need to solve the different way. And so let me see which is better. I just present the way on the bottom and omit the top method or both method. There's not so much time, just 30 minutes. For now, I need to finish this in 30 minutes, less than 30 minutes, for one of the reasons of my private watching TV shows of K1 or something. Today is September 28th, or Sunday night in Japan, and I need to calculate these values, delivering these values. So I'd like to omit this case because it's already in the textbook. But in both cases, the matter we need to, in both cases, is firstly presented here. We need to present it. Need to be presented by me and my, which is my output to be in voltage gain of the feedback common source amp here. What's the voltage gain? So just a minute. So at first we need to correct the information for solving this problem for getting VN squared bar and IN squared bar. Those are the information needed for four-step procedure written in this textbook. One is component value. There's RF, so RF has 4kT, R voltage noise squared bar, or in another expression, RF. This is RF, R sub S, R 4kT over R sub F of noise current of R squared bar, and there's M1 which is 4kT gamma GM equals I N M1 squared bar, current noise, channel current noise to drain to source, and going to drain to source, or in other words, using lemma 2, which is explained later on this example 713, finish it, which is says 4kT gamma over GM is input referent voltage noise squared bar. These are the components for device noise, and I1 doesn't have noise, ideal one, and the transfer function, we need to get transfer function if it is AV, V out over V in the absolute value. For this, we need to write down the equivalent circuit, small signal for small signal. Small signal I1 is DC and no opened, can be opened, and RF and V out, and channel MOS, and there's V in. V in is applied, plus minus and ground, and V drain to source, there's a channel current introduced by B in. The value is GM B in, and if input current I defined by this direction, this is RF, the KCL, Kirchhoff current law, is written as this, and B in minus B out divided by RF equals the same GM B in. From this we can derive our GM RF minus 1 or minus GM minus 1 plus GM 1 minus GM RF AB equals minus GM RF minus 1 from this. This we need this value and these values, and we sum up these non-correlated two values to get total noise, Vn total, to get non-correlated iso element noise squared bar or current. Now this is in intermediate procedure of the solving the problem. I will do this in intermediately in the meantime in solving this problem. And 4 is spectrum of output is to be this transfer function squared times spectrum S in. This is S in. The S in times AV squared is V S out. S in equal when voltage. This is voltage. Squared per square root hertz per hertz. And volt squared per root hertz. Power per 1 hertz. And in current, ampere squared per hertz, this is AI squared. Current gain, we need to use current gain when using top method, input shorted method, and which is described already in this textbook, I out over I from lemma 1 and V in GM, conductance GM times B in equal I out. When output shorted, current is go up in this direction, and the circuit has conductance GM and B in is applied. This relation is generally applied, and using this we can get GM and I from the topology, also I out, and we get I in. This is the top method. So this time we omit this case, just giving to these four. Okay, so output opened. When output opened, as this textbook beforehand, we understand output opened. Vn is floating, and voltage, input voltage noise is no interference, no effects on the circuit, and just current noise In squared bar is affects this circuit and affects the output voltage or current. So we need to open and short method both to get these values in each cases as written in the top cases. In input open cases, we need short open cases models to get both data. But first, input opened model is described as this open RF and output also shorted, and this is I out I out open cases suffix input shorted voltage 1 and 2, suffix is 1 and 2, this is suffix I and 2 of out scaled bar is coming in, and this is channel, this is open and can be generated affected by input current, but we don't know input current here. And this is RF, and this is voltage. Not the, but we need current expression for this, and this current is IN R squared bar equals 4kT over RF power is. Now this is 4kT gamma GM. Before this, I said before gamma. What is I didn't say gamma. Gamma is number is 0.666. Magic, the demonic number. Actually 666 into infinity, which is 2/3. 2/3 is not easy to remember, but 666 very easy to remember. So 0.66 is recommended, or 0.66 is weird and feeling uncomfortable. So you say 0.67 immediately. You use 0.67, but remember 666, 0.666, 2/3. Gamma is applied these numbers usually, or sometimes just 1. Written in this textbook, which is written. These are written in this textbook, so I don't mention that. I didn't mention that, but we need to this gamma for NMOS and PMOS. So current is this is I and M1 scale bar. This is 4kT over RF plus 4kT gamma GM. Well, so what the V in? But this is no. This is if this is shorted. This is for this false, and this is suffix 1. So this is open. So we can't write it. We can't use this, and V out is open, and we need V out noise 2, and V and 2 of output squared bar is what? It's open. When it's open, there's no voltage noise applicable to input, but from lemma 2, after this example explained, there's VNR squared bar equal 4kt RF, sorry, not 4kt over RF. And this is virtual, this is transferred, which is transferred to divided by gm squared. Divided by gm squared means v in m1 squared virtually appeared, and that equivalent circuit means v out equals this noise in series with this noise. So vn r squared bar plus vn m1 in m1 squared bar. This is derived by lemma 2, which is 4kt gamma gm divided by gm equal 4kt gamma over gm. And this is 4ktr. So vn2 out square equal 4ktr plus 4kt gamma over gm. Then what's next? We need to calculate this and this, and using this we can get this, and using another input shorted cases applying and using voltage gain, we can derive for the expression for Vn in squared bar. This time using input opened model, we can generate this, because when opened, input opened and there's RF, and RF opened, current going through this, and V, this is RF, but this current equals GM V. So the input R input resistance or input impedance seen from input is just like the diode connected cases, just 1 over GM. Even though there's additional device RF is inserted here, but the current going through the channel is, all current is going through this from voltage source, and there's no they assume to be no parasitic capacitance or leak passes there in gate. So this is just like this, just the same as this one. Resistor looking into the drain is 1 over GM. So R, we know R in very easy, and I in we know I n in squared times R in squared is a voltage drop V, which is Vx or n channel, and this is Vx, not Vx, and there's I noise in squared bar I in, and Vx I in R in, there's R in, which is 1 over GM, and feedback is there, and there's a voltage gain. This is transfer function of AB equals the absolute value equal GMRF minus 1. So squared is this. V in, this is V in power, and times GMRF minus 1 squared equals V out. Vn out squared. This noise equal the same noise. Represent the same noise in another way. Because both of this is input opened case. Input opened and generate current, and injected R in, and they generate voltage and generate the output voltage when time multiplied by voltage gain. So both same model, same output noise, which is 4kT R plus 4kT gamma mod GM, and R in equal 1 over GM squared, 1 over GM squared. So I n input squared, input referred noise is then given by GM squared 4kT R plus 4kT gamma over GM divided by GM RF minus 1 squared, which is equivalent, the same as the one explained in textbook using another method. Which is 4kT R squared AV equal And what are V out, V and in? We need to short the input, and the same as the solution or in the textbook. In this case, using suffix 1 voltage noise, input shorted, short RF there, and we need to find R out, and I out noise IN2 input shorted cases, I out 1 out squared suffix 1 out squared were times R out square equals Vn1 out squared. This divided by AV squared is actually the Vn in squared bar. The AV here equals GMRF over 1. Already checked. And R out equals input shorted, so there's no current, infinity, lambda equals 0, just R out equal RF. So this is RF squared. So RF squared IN out squared divided by GMRF minus 1 equals input referred noise power. The IN out squared bar is given how is the same as the solution using method 1 written in this textbook. Input already also shorted, but we don't use transconductance for this time. This is current noise of I mistakenly written T over F, and this is channel current noise T gamma GM in this direction. So this IN1 out squared equals this plus this. So this is, in other words, 4KT over RF plus 4KT gamma GM times RF squared divided by GM RF minus 1 squared, which is, these are the same results. Maybe sanity check. I'd like to check the textbook. What is this? Is this correct? If this is correct, I can finish this recording to explain the another method to derive the expression for input referred noise and current referred noise of R feedback common source amplifier, having M1 transconduction GM and lambda equals 0. And the results, Vn equals 4KT over R plus 4KT gamma GM divided GM minus 1 over FR. So we need to check and transfer the expression. There's no RF squared in here, but this representation is like this, divided RF squared divided RF squared. So this is going to be banished. This is going to be RF GM RF minus all over squared, which is GM minus 1 over RF squared. It is the same. Okay, checked, done. And IN for IN I sub n in squared bar, it is 4KT R GM squared plus 4KT gamma GM divided by this. Okay, this is also the same. Okay, so we now finished. Input opened model used with lemma 2 of conduction GMB in okay, no, V in squared equals GMB I out squared IN out squared divided by GM squared. Input referred noise is derived from output current noise in CMOS. This is lemma. This lemma and input out or input opened model using this, we can get ion in, and input shorted model we can get Vn in squared. Of course, before this, we need to follow the 4-step procedure, finding components noise and correlated cases is judged, and find the transfer function in these. Generally speaking, these are voltage gain, and also is DC voltage gain, considering only for low frequency noise, and sum up the components noise non-correlated and use a spectrum times transfer function leads to output spectrum. So behind these method, we every time using we need to use 4-step procedures written in this textbook. You already know. Okay.